Professor Jing is online.
Yeah, now the towers.
Okay. I'm waiting for Professor Rai.
Yeah, I guess so.
Can you see my screen on Zoom? You can.
Okay.
Yes, we can see it on Zoom.
Yeah, we can hear him too.
Yeah, that's kind of cool.
Professor Wright is here, yeah. And Professor Jing is also on.
Oh, okay.
Zoom.
Then we have the committee. We should go.
Okay.
He's just connecting, so
All right. Give a second then.
I think he's.
All right. Ready?
Yes.
All right. Well, thanks for coming out on this beautiful May day. I'm excited to hear and share with you Ammara Talib, who many of you know, but for those who don't, Ammara is a PhD student in civil and environmental engineering, but is advised by my lab, and so she's had this dual life of living between atmospheric science and civil engineering. And today she's going to talk about some of her work, but by way of background, Ammara got her bachelor's degree in Earth and Environmental Sciences from the University of Punjab in Lahore, which is a beautiful city, by the way. I've been there. Where she worked and did an undergraduate thesis on environmental impact assessment for power companies. And then later on in Pakistan worked as a high school teacher. I had forgotten that. And also interned in some environmental protection organizations. But shortly after that, she was able to secure a Fulbright fellowship and come out over to the University of Massachusetts Amherst, which I drove by 5 hours ago, where she got her master's in environmental conservation and a thesis titled Assessment of Impacts on Land Use, Land Cover Change, and Climate on Water Resources in the Massachusetts Watershed. That has been a pretty successful ongoing collaboration. It's led to several publications on climate change and land use, one of which already has 51 citations, and 3 additional first author papers, including one even coming out this year, on contaminant management in watersheds. She then came over to the University of Wisconsin-Madison in civil engineering to do her PhD, but she was a little unsure about where she wanted to go, and she reached out to me after thinking about what she wanted to do with her degree and said, hey, I'm thinking about maybe switching. She sent me an email in November from CE at Atmospheric Sciences. I was like, well, hold on, let's talk about what you're interested in. And so then a month later, she actually sent me proposals. And the 3 proposals were how to forecast hydrologic flows in different locations, hydrologic models driven by satellite-based precipitation, and regional evaporation estimates from flux towers and satellite data. And I think what you'll see is that in many ways what you're hearing today is kind of a merger of the ideas that she pitched back when she started with me a few years past. Very fortunately, at the same time, we had just got in a inquiry from the State Department of Natural Resources and the Wisconsin potato growers about this question about water security in the central sands, which have faced several droughts, which you'll hear about, and whether we could make reliable measurements and forecasts of future flows. And so we kind of glommed onto that, and Ammara's PhD has been really focused on using observations and models in that area, which has already led to 3 publications and then 1 lab-authored paper, and then there's also, she just submitted another paper and has a 3rd one in preparation based on that work. So a pretty productive period that she's been here. And very much on the ground floor of this project with the central sands and understanding water supply from a measurement-based perspective. And so it's my pleasure. There's also cookies I can pass around. I know it's kind of non-standard time, so if you need sugar, I need sugar. But the title of today's talk is Prediction and Forecasting of Evapotranspiration and Groundwater, along with improved parameterization of evapotranspiration, or ET, in agricultural lands. I'll turn it over to you.
Thank you, Professor, for the introduction. Hi, everyone. My name is Ammara, and thank you all for being here for my presentation. Today, I will talk about my dissertation. The topic of my dissertation is prediction and forecasting of evapotranspiration and groundwater anomalies, along with improved parameterization of ET in agricultural lands. So So I will start my presentation today with motivation and background and overall research scope of my research. Then I will talk about 3 different parts of my dissertation, and I will end my presentation with summary, implication, and future work. So let's start with motivation and background. Evapotranspiration and groundwater are vital components of hydrological cycle. Evapotranspiration not only connects energy and water cycle, but it also is a leading indicator of groundwater extraction. For example, when water is withdrawn out of the ground in form of irrigation, then some of that water is evaporated in form of evapotranspiration. Irrigation is very vital for agricultural productivity, and it uses around 70% of the total water withdrawals from both surface and groundwater across the globe. Irrigation is not only important for agricultural productivity, it can also have other effects. For example, irrigation can influence our local to regional atmospheric processes and land surface interaction by altering the precipitation and partitioning the latent and sensible heat fluxes. Now, if we go back to, again, agricultural areas, when water is withdrawn from agricultural areas, then it can lead to water depletion. And we are aware that in the past couple of years, we had recurring cycle of wet and dry years. And now, because of irrigation-induced stress, even during normal to wet years, that depletion of groundwater still persists. That's why it is very important to conserve the water and understand the dynamics of both evapotranspiration and groundwater. Because of human-driven influences and climate-driven influences, there has been a lot of stress on water resources. For example, you can see the drying of Little Provo River, that is in Wisconsin Central Sand. That is one of the highly productive agricultural areas in Wisconsin. And in 2010 drought, you can see the effect of that drought in the Little Provo River. Now, because of the climate-driven and management-driven demand of water, we are interested in understanding the dynamics of both groundwater and evapotranspiration. Evapotranspiration is this second leading component of the land surface energy budget, but it also least constrained term in the energy budget. It's because it's very hard to measure and estimate. Additionally, groundwater is also very hard to measure because of subsurface heterogeneity. Now, there are direct ways that we can use to measure evapotranspiration. For example, we can use eddy covariance towers, or we can use piezometer to measure groundwater. However, there is a cost associated with these direct measurement because of their fine spatial and temporal scale. Because like here in these figures, you can see that they are scattered across a big area, and we might miss some of the areas if we want to study a big region. There can also be some indirect methods that we can use to measure these 2 different components of water cycle. For example, we can use remote sensing products, but then remote sensing products have their trade-offs. For example, coarser resolution, cloud problem, and their revisit frequency, and then different model assumption can lead to different kind of estimates or uncertainty in the products. We can also use process-based mechanistic model. Now, process-based mechanistic model can be useful and can provide us useful insights about groundwater and ET dynamics, but those process-based models depend on meteorological forcing data, topography information, geology information, and some land management information, for example, crop rotation and irrigation or human-induced drivers in that area. So it can be computationally expensive to calibrate those models and use them for a bigger region. So there has been interest to use data-driven empirical models. However, there hasn't been a lot of studies where those data-driven model has tried to understand the dynamics of both evapotranspiration and groundwater on a regional scale. And also, there are only fewer studies that can look at the importance of different drivers like climatology-related drivers, topography, and human-induced driver. So that leads us to the research scope of this dissertation. The overall objective of this research is that we want to apply new observation and modeling tools to better understand and forecast the dynamic of evapotranspiration and groundwater in agricultural regions, especially those facing water stress from drought and increasing water withdrawals. So with that overarching goal, I will be talking about three different components of my dissertation today. So the first component is about improving parameterization of so here I will be evaluating a regional evapotranspiration or potential evapotranspiration model. While it can be useful to focus on a model on a regional scale, we are also interested in broadening our research scope and focusing on agricultural region in Midwest, and that will be the second part of my dissertation. Then in the last and third part, I will talk about the spatial and temporal dynamics of groundwater. So let's start with the first part, which is about improving parameterization of a regional ET model. So our study area for this part of the dissertation is Wisconsin Central Sand, and you can see this boundary in the black color, and these red dots are the high capacity irrigation wells that are used to withdraw groundwater, and there are thousands of these high capacity wells. And because Wisconsin Central Sand depends on groundwater for their irrigation, and we have $550 million food industry that depends on this region. So the growers get their estimate of ET from a regional model called Wisconsin Irrigation Scheduling Program, or WISP model, and they get email if there is a consistent high ET, and then based on those emails, and they can plan to irrigate their fields. So by folks, the specific research objective for this part of the research is to assess uncertainties in the WISP model, inputs due to the meteorological variables, because even though WISP has been used to estimate ET, it hasn't been evaluated for its performance based on ground truth data. And when I started working on this, I didn't know that what are the causes of uncertainty in this model, whether those uncertainties are due to model inputs, or whether those uncertainties are due to some parameters that model uses. And then once we figure it out, that uncertainty in this model, the second goal is to improve model performance by calibrating parameters based on ground eddy covariance observation and satellite measurements. So just a little bit background about this model that growers use in Wisconsin Central Sand. WISP is based on a Priestley-Taylor model of potential evapotranspiration. So the model outputs potential evapotranspiration, and then a canopy model is used to convert potential evapotranspiration to actual evapotranspiration. So here we can see that our slope and psychrometric constant, and then our R-net. Then there is also some empirical equation that WISP uses to find different components of energy balance equation. So we have this equation for the long wave net, where it uses upward long wave, clear sky emissivity, Stefan Boltzmann constant, and then this clear sky ratio. Now, one term that I would like to focus is this clear sky emissivity, which is based on this its empirical model. And if we look at this equation, you can see it can take a form of like linear equation. We can have this as our intercept, we can have this slope, and this can be our x. And then ITSO model has some estimated parameters for A1 and A2, and these parameters were estimated based on synoptic measurements taken in Arizona in 1982. And then WISP is also based on these. WISP also uses the same coefficients. Now, in order to find out the uncertainty in this model, we set up different observation sites in Wisconsin Central Sand to take meteorological and eddy covariance observation. So in this map, you can see that I have labeled some site as a training site and some site as validation site. When I'm saying training sites, not in this part of the research, I'm not using any data-driven model. When I say training site, it means that I used data or observation from these 3 sites, which is US CS1, 2, and 4, to see, to first evaluate, okay, what is the source of uncertainty. And then, let's say if we find a source of uncertainty, we correct it, then I can use remaining 6 sites, which are labeled as with this pink color. I can use those remaining 6 sites to evaluate the WISP correction. And you can see that 2 of those sites are actually outside of the boundary of Wisconsin Central Sand. So 5 of these sites were a part of my PhD, and then from other sites I got data from Ameriflux. And here is a zoom of those 5 sites. And different type of crops are were grown in those sites during the period of 2018 to 2020, and we are focusing on the growing period. And we use different instruments, for example, ultrasound, dual sonic, and infrared analyzer, anemometer, LICOR, and then basic meteorological sensor to calculate fluxes and other observations like vapor pressure, air temperature. And also the reason of estimating these variables is because WISP inputs include air temperature, vapor pressure, and incoming solar radiation. And flux measurement were taken at 10 Hz frequency, and then latent heat was used to compute actual evapotranspiration data, and then it was compared with this actual heating. Okay, so first what I did, I compared model observation, model inputs with our observation. So I started with air temperature and vapor pressure. So in this plot, on the y-axis you can see air temperature, and on the right side of the y-axis you can see vapor pressure. So observation are shown with green color. I use light green for temperature, and I use dark green for vapor pressure. And then this orangish color is for WISP inputs, the inputs that go into WISP, and WISP inputs are based on satellite data. So if we look at these evaluation statistics, we can see that there is a good agreement based on the percentage bias and mean absolute error, because we have a very small bias and small mean absolute error. The third input that WISP uses is incoming shortwave radiation from geostationary satellite. And looking at the evaluation stat here, we can see that there is a high agreement between observation and WISP inputs in daily time series. So it means that model uncertainty is not because of model uncertainty in the model inputs. So then what I did, I started looking at the inside of the WISP model. So I looked at what else I can check. So I looked at long wave net radiation. On the y-axis you can see long wave net radiation. Here observation is shown with dark blue color, and the tan color is for our model output. I mean, WISP does not directly output long wave net, but if you put all the equation in your system, you can get long wave net. And if we look at percentage bias, you can see a high percentage bias. And it looks like this model is underestimating long wave net, because if we look at this plot, you can see, okay, how low our observation are going. It's around, you can say around minus 130, but WISP is giving me a lowest value around maybe -1, -67. So it is underestimating long wave net. So then when I looked at the long wave net equation and looked at what parameters there are, the lack of agreement was traced back to the atmospheric, clear sky atmospheric emissivity. Now going back to this original equation, because long wave net depends on this clear sky emissivity. And you can see that before correction, these are the parameters. And the plot I showed you before was from my 3 training site or evaluation site. Now this plot is from my validation sites, because let's say we figure it out that maybe model uncertainty is related to this one part, like maybe that one, correcting that one part can help with some of it. So here I am showing different, the remaining 5, so 6 different sites, and I use different colors for these sites. However, I calculated these evaluation stats for all of this data combined, and on the y-axis you can see my WISP long wave net, on x-axis we have observed long wave net, and you can see that yes, there is a underestimation of percentage bias. So what WISP model does, it uses an assumption that if we have clear sky condition, then our long wave in is equal to long wave out. So using that assumption, we calculated our own emissivity. I call it observed emissivity. Even though tower does not, or flux tower does not directly give us clear sky emissivity, but it does provide us true long wave in and out. So using that, I computed observed emissivity, and then I use this computed observed emissivity as my y variable, and then try to estimate these parameters by treating this equation as a linear equation. So when we did that, after correction we got these variables, and then here is the plot after applying the WISP corrected long wave net, and you can see based on this evaluation stats that percentage bias has reduced. Now if we reduce the percentage bias in long wave net, let's see how it affects evapotranspiration. In this plot, my observed evapotranspiration is in green color, and then WISP estimated actual evapotranspiration without correction is in purple color. So let's just look at stat in purple color, because that's how model is doing before correction. So you can see that we have high bias before correction, and that's my evaluation side, it's not the training side. We have a percentage bias of around 35%, and my model is overestimating evapotranspiration. But after correction, you can see that our percentage bias has reduced, and that also helped in reducing our mean absolute error as well. Now, just by looking at model performance on training side by month, you can see I'm showing Rs here on the y-axis. So even let's not just pay attention to on the correction yet. You can just look at WISP evapotranspiration without correction, that is in orange color. There is a high correlation that is found between observed and WISP evapotranspiration during the later part of the growing season. So you can see in July and August. Model generally is doing well compared to the earlier part of the season. I think it's because WISP use another assumption that when canopy cover is 80 or greater than 80, then potential evapotranspiration is equal to actual evapotranspiration. And before that, it used a canopy cover equation to reduce the evapotranspiration. So there might be some uncertainty coming from that, and this performance gets poor during those shoulder time, or when we don't have canopy cover above 80%. So overall, you can see that R-square is not improving that much after before and after correction. But if we look at NSC value or Nash circuit value, we can say that NSC was significantly improved during June, July, and August, because you can see that after correction, that green box plot went up, or Nash circuit improved. And by looking at mean absolute error, we can say that okay, mean absolute error for July and August was reduced, because you can see the green box plot coming down. Then by looking at percentage bias, we can see that bias was also reduced in all months, but you can also see that used in July. Specifically here we have a little bit more overlap. Okay, now next I'm just showing the cumulative evapotranspiration for Wisconsin Central Sand region for the growing season of 2020. And I'm also showing all the sites we have. Since that was 2022, so we are already in our evaluation time, or you can say that testing period. So before correction, you can see the range of evapotranspiration is 501 to 554 millimeter. After correction, you can see there is not really even an overlap. There has been a lot of reduction because before correction we have ET right here, and then all this ET is coming after correction. And then in the next plot I'm showing the ET difference. So we can say that a difference of 128 to 140 millimeter for one growing season has implication for water conservation for growers, because if they are getting if they get estimate of ET in email that ET has been really high, then they probably will plan to irrigate the water, and it's possible that model might be overestimating ET, and it wasn't that high of an ET. Okay, so now moving away from our regional ET model, we are increasing the scope of our research and moving toward the Midwest. You can see that for this part of my dissertation, this is my study area. We are including agricultural sites where we had observation of actual evapotranspiration in Midwest. Okay, so the specific research question I'm asking in this part of the dissertation is how well can empirical machine learning model predict and forecast evapotranspiration 3 days in advance in irrigated and rain-fed agricultural lands. And what are the important drivers for predicting and forecasting evapotranspiration 3 days in advance in irrigated and non-irrigated areas? So here now I'm going to talk about machine learning model. In the previous part, we just used observation to parameterize the regional model. So here I'm interested in building a sim model for evapotranspiration prediction and forecasting. So first I decided, okay, let's look at some simple variables that in most of the empirical equation we use, like we just saw in WISP model, where usually we use like air temperature, information, vapor pressure, and some energy budget information. So what I did, I used these 5 variables or predictors. So in precipitation, you can see that I have 7, 15, or 30 days moving average. For my simplest model, I'm just using 7-day average. So I'm just counting it as one variable, not 3. So right now I'm just counting this precipitation as 1. So by using these 5 predictors, I built a very simple model, and I call it RF5. RF based on random forest, because that's the algorithm I used learning, and RF is ensemble learning algorithm. So LSTM is long short-term memory. I will talk about it. So I built those 2 simple models. Then we thought about adding more complexity in the model. We added 15 and 30 days moving average and wind speed and some information about the biophysical characteristic of our crops. And that led us to make a little bit complex model with 11 variables. I called RF11 and LSTM11. And then the third last version of the model, that was the most complex with 16 variables, and there were 2 versions of it, one based on random forest and one based on LSTM. So I used these predictors and then build a model, one based on deep learning, recurrent neural network, which is LSTM. The reason I used LSTM because compared to the traditional feed-forward machine learning algorithm, long short-term or LSTM model deals with the problem of back propagation or like gradient loss problem. So it doesn't deal with that, and it can solve that problem. So what I mean by that sometime when you're too advanced in your time period, it's possible that you might need some information from the previous time step. But if you're very much close to your output layer of your model, then model will not remember the information, and there will be a loss of information. What LSTM does, it has a forget gate, which you can calibrate some parameters related to that gate, and then you can train your model to see how far in back model wants to see to remember some of the information. So I use this LSTM model, and LSTM model has different neurons. All these input predictors will come into an input layer, that's one of the layers of the model. Then model will connect those input layer with hidden layer where there are different neurons, and in all of those neurons have this setup: input gate, forget gate, and then output gate. And then based on different equation, a connection will be built between input and output. And then LSTM will try to understand the nonlinear relationship between your predictors and your output. Then random forest, which is not a deep learning, it's a ensemble learning based method. What it does, it builds different trees by subsetting the data and subsetting the predictors, and model in such a way that those trees try to explain variance in your model. And then what model does, once you calibrate it, it take an output based on the majority vote or based on averaging the output from different trees. And then we can calibrate the model based on how big of a tree you want, how small the data split should be, how small the leaf nodes should be. So all these parameters can be used to calibrate the model. Another benefit of random forest is that it can help us to determine what are the important variables in our system. What it does, it holds some variable constant and then permute each variable one by one, and then see that by excluding or including one variable, how much reduction in mean square error, and then it rank those predictors based on that reduction in error, and then we can get importance. Okay, maybe this predictor is more important than this one because once we removed it, error got bigger. Okay, so after setting the layers and everything, trees model can be calibrated, and then after calibration, model validation was done, and then we have estimates of ET prediction. As I said, since I was using different version of model, I also had different version of outputs. And then we were also interested in forecasting the evapotranspiration, and for that part of the research, we provided our model with forecast methodology, and then we got ET estimate like 3 days in advance. Now a little bit information about the time step that we used in this research. We used a daily time step from 2003 to 2019, and we focused on the growing period. There were 19 sites. 14 of them were rain-fed and 5 were irrigated sites. And then we used 70% of the observed data, which was around like 18,000 daily observation for training the model, and then rest, which is around 8,000 observation to validate the model. And then again for calibration, we used 13 sites, and then run time for different type of model. So here I'm showing the performance of prediction model on the testing data. So on the top panel, I'm showing results from the complex model that used 16 variables. On the top panel, I have random forest results for different crops like corn, soybean, potatoes. On the x-axis, I'm showing predicted ET, and on the y-axis, we have observed ET. So what we can see that there is a good agreement between predicted and observed evapotranspiration. For example, for RF model, the R-square varies from 0.53 to 0.70. So that 0.53 is coming from potato. At that time, I think I had 1 season and 1.5 seasons, so smaller values. And we noticed that RF can be very sensitive to the size of the training set. So it has higher bias when we have smaller data set. And then we also calculated Wilmot scale score, which was around 0.85 to 0.9. And then LSTM had lower bias for potatoes, but then overall LSTM has higher error. So if you compare the error between a random forest and LSTM consistently had higher error. Okay, so here I'm showing one of the validation site, again a testing site. I'm showing the time series plot, and my observation is in black, and then green is my LSTM model, and blue is RF, and we can see that model is able to predict the interannual and interseasonal variability. And then consistently RF performance was better than LSTM, and then we also have empirical distribution where you can see an overlap between both models. Then we also looked at the importance of different drivers, and the importance of drivers is scaled. So if you add the importance from all the variables, that should be equal to 1. So based on that, we can see that vapor pressure right here, and crop coefficient, which is right here, they were the most important predictors for irrigated crops. We also found out that for non-irrigated crop, shortwave and enhanced vegetation index were important predictors. We also compared the performance of our model with NLDOS NOAA ET. Even though NLDOS has lower bias compared to our model. The error of NLDAS was higher compared to our model. So I think the NLDAS has higher spread because it tried to average ET for a larger geographical area. Okay, now just to the second objective of this part of the research, we were also interested in looking at the forecasting of evapotranspiration. So here I'm showing different lead time for ET forecast. We have like ET, what is the ET tomorrow, like 1 day in advance, ET in 2 days in advance, or ET 3 days in advance. And we have on our, so here I'm showing the ET on like daily ET, but then that was averaged on a month scale. And since I use this forecasted meteorology, so the forecast meteorology is usually always in ensemble. So in my case, it was like 11 ensembles of meteorological forcing I got. So then I also had 11 estimate for my forecasted ET. So then I have used that ensemble, different ensemble to calculate the standard deviation and just plotted it here in the screen. You can see that. So observation is red, and then forecast is in black. And then here we have LSTM. So you can see that again, RF performance was better than compared to LSTM. What we can see for LSTM, as lead time increase, there is a slight increase in mean absolute error. For example, it's like 0.77 to 0.8 right here, if you can see, when we are forecasting ET like 3 days in advance. Mean absolute error for June, July, and August was higher, which was in concordance with higher variance on the GEFS meteorology ensemble forecast spread, because I got my data from GEFS. Overall, RF forecast model performed better than LSTM, but LSTM was more reliable because you can see that ensemble spread is closer to the observation. We also calculated importance of variable for our ET 3 days in advance, and we found that vapor pressure, solar zenith explained about 32 and 12% variance respectively in the model. There were also other important predictors. So for example, what will be the shortwave radiation the day when we want, for the day we want to get forecasted ET. So that makes sense because it is energy limited area. Okay, that leads me to the third part of my dissertation. So here we are focusing on groundwater dynamics. So a specific research question I'm asking is that how can easy to obtain remote sensing drive environmental data sets can be used to accurately forecast groundwater anomalies across densely irrigated regions by using machine learning models, and how do groundwater anomaly forecast vary in space and across the Wisconsin Central Sand region. We are also interested to know that how can irrigation pumping and crop type change can influence anomaly forecasting. So here we were interested in again building up a model to forecast groundwater anomaly. So I called one part of my data set as dynamic or temporal data set because it varies in time. For example, that's what we expect from climate data. So I had 11 climate-related covariates, for example, maximum mean temperature, wind speed, precipitation, and evapotranspiration. Then we also needed information about the water balance, for example, like soil moisture, runoff, or snow water equivalent. And I had 3 covariates. Now we are talking about groundwater, and it is very challenging to estimate groundwater dynamics. So I wanted to give my model information about topography and morphometry data. And I called it spatial and static data because we had observation for 26 different sites in Wisconsin Central Sand. So for those, I wanted my model to also know that, okay, there are different regions. There is a spatial heterogeneity. And just going back to that topographic morphometric data, these covariates I derived from digital elevation map. I use train analysis, and I also use distance to rivers, and then that gave me information about surface roughness or wetness accumulation and information like that. Then I also provided my model some information about soil type that it has, and I had 5 covariates from that. Now just looking at the time series, or the time period that we were interested in, We were interested in the long-term time series, so we were interested in time from 1958 to 2020, and we had 26 location, as I said. Now, as I said, that we are also interested in human-derived or human-induced drivers. That is related to like land use, land cover change, and groundwater pumping. It's just in Wisconsin, growers started reporting groundwater pumping data from 2010. So I had to make a separate model, on a smaller time period, because that's the time when I had groundwater pumping data, and I had 7 wells that I could use, because not all wells have same time series. Some wells have data for 2 years, some wells have data for 10 years. And then one last important thing is boundary condition. We didn't use boundary condition in our ET modeling. I'm sure estimate would have been better if we use like some boundary condition there, but in groundwater, boundary condition is very important. And I had gone covariate for that. Now you can see I have a lot of covariates, and there can be correlation in those covariates. So in order to reduce the dimensionality of that data, we used PCA. And when I did PCA, then instead of using 7 covariates, I picked 7 PCA. The first 7 PCA that can explain most of the variance. And I didn't need to do PCA on some of the drivers. For example, here I only have 2 covariates, just land use and groundwater pumping. So I didn't do PCA here. So after doing PCA, model input was provided to the input layer of LSTM network. And then again, this input layer then transferred to the first layer of the LSTM, and then to the second layer of the LSTM. I also had a dropout function in my LSTM model to reduce the problem of overfitting. And then after providing all this information, we expected an output layer. Now there were different versions of model I made. One was temporal model. I call it temporal model because in temporal model, I'm using one part of the time series from each well for training my model, and then the later part of time series for testing my model. Then I also develop a spatial model. In spatial model, instead of using all 26 wells, I use 18 wells for training the model, and then 8 wells for testing the model. And then a shorter version where I wanted to look at the human-induced drivers. I use like model based on 21 covariates. As you can see, there are fewer wells, so spatial data information that I provided was also smaller, so less covariates. Okay, so model was developed, it was calibrated, and here I'm showing the performance of the model on the testing data. So on the x-axis, I'm showing the observed anomalies, y-axis forecasted anomalies. I did not develop a separate model for shallow or deep wells, but I'm just showing the estimates based on different colors to just distinguish between shallow and deep. I calculated these evaluation stats for all of the data set, including both deep and shallow. We have a R-square around 0.84, but we can see a higher spread on for the shallow wells. So it looks like model performance is better for deeper wells than shallow wells. I thought other way around. I thought because it's a shallow well, so it should respond to any change in precipitation or pumping quickly compared to the deeper well. But it looks like model simulation for the deep hydrology was more smoother than the shallower one. And then in the next plot, I'm showing my mean absolute error across all these 26 locations. Our mean absolute error ranges anywhere from 0.07 meter per month to 0.27. And just to remind, I'm forecasting groundwater 2 months in advance. So if we just focus on like 2 of these wells, one thing I noticed that mean absolute error was not always correlated with large sample size or autocorrelation, because that's one of the criticisms sometimes data-driven model get, that okay, if you have trained your model on a larger sample size, your error should be lesser. Or higher autocorrelation will help you because you're providing it a previous boundary condition, so it should, if there's a higher autocorrelation, the performance should also be better. But that was not always the case. We did not see that. For example, let's look at well 4501, and this code is coming from USGS unique ID, so I just use that to identify a model. So if we find well 4501, that's right here, it's a darker color, so darker color mean higher error. However, the autocorrelation is higher compared to this other well where autocorrelation is lower, but then even though autocorrelation is lower for this well, which is lighter, in lighter color, so it has also less error too. Here I'm showing a plot between autocorrelation and mean absolute error, so you can see that even though well 4501 has higher autocorrelation, the error for that well wasn't lower, it was higher actually. So that one interesting thing we noticed. And we didn't see any obvious spatial clustering in like where we can see, okay, in one region we have all the dark wells, or in one region we have all the lighter wells. So I think maybe we can say that probably we did not miss a key predictor here. I mean, we can see it's like kind of scattered all over. And right now I'm showing a time series plot for one of the evaluation sites. So I picked a well. Again, you remember 4-5 from the previous one. I picked the best performing well based on R-square and NSE. So that well came up. Okay, so here you can look at R-square. Then I picked a well with lowest R-square. So we got this well with lowest R-square, which is 0.33. Now, one thing we can see that R-square and mean absolute error were not correlated. This well has higher R-square, but does actually have higher mean absolute error. I should expect, okay, it is less biased, so probably it might be more accurate too, but that wasn't always the case either. What I noticed that R-square was correlated with variance anomalies. For example, in this plot, you can say that I'm seeing anomaly variance on the x-axis and R-square on the y-axis. So you can see a correlation here. For example, this is a model with high R-square. It has also higher anomaly variance. So it looks like if there is higher variance, model become less biased. But the mean absolute error reduced. Mean absolute error was higher if there is a higher variance. It could be because if there is a higher variance, model previous by t-1 time step is not more correlated with the t time step because there is a higher variance. So that could be one reason I was thinking. So you can see that higher variance, higher R-square, low variance, lower R-square. And then here I'm showing the well with moderate performance, and you can see it's kind of in between these two because its R-square and variance is in between these two wells. And as I mentioned in my methodology section, we also had a spatial model. I found similar trend in my spatial model as well, and model was able to learn regional transferability. It was able to provide good results. Now, one part of this research was I wanted to see effect of drivers on forecast. So what I did, I took my model that's already built up and I started extracting variables. Like if I, let's say in this model, if I remove snow water equivalent, and if I remove information related to topography or meteorology, how the model performance will reduce. And that can tell me the importance of variable, or it will give me some information. And then I reported the percentage change in mean absolute error after removing that variable. So this delta sign mean I removed this variable. So if we start with our snow water equivalent drivers, if I had one driver for snow water equivalent. So if I remove that, I can see that for 6 wells, my mean absolute error percent increased by 10%, more than 10%. And the increase in mean absolute error was anywhere from -32 to 46. So positive value mean the error reduced in some location, and negative mean the error reduced. So the 3 locations where the error reduced the highest or the significantly were these 3 locations. And then if we look at model without topography, I noticed that after removing topography information, for 10 wells, mean absolute error was greater than 10%. And the places with highest error was these 3 locations. And then similarly, I did with meteorology, and we got these locations with highest error. And after removing soil information, we got these three positions with highest mean absolute error. Removing boundary condition, as I mentioned, that's very important for groundwater. For all of the wells except one, mean absolute error increased by 10%, and then especially these three locations. So by looking at these, the effect of removing different drivers on the percentage change in mean absolute error, we can say that due to the higher spatiotemporal variability, the drivers have a strong but variable and site-specific influence on long-term groundwater changes. Now the last thing that I wanted to check is the effect of human-induced driver. As I said, the model that was built was for a shorter period, 2010 to 2020, and I wanted to see the effect of land use change and irrigation and pumping effect. So here I built a base model where I did not provide information about land use and pumping. We got, this is our testing sites, and we wanted to see, okay, what is the R if we don't provide land use information and pumping drivers? It's 0.41. Let's see if we provide that information. So what will happen? Model performance improve, and especially there is an improvement in the negative anomalies, which is more related to the shallow groundwater. You can see here, like here they are on top of each other, so this negative anomaly improved. Now just looking at how it affects R square and NSE value, you can look at the y-axis where I provided percentage change from baseline model. If we only provide model with land use information, the percentage change in R square, the R square improved like 9.2%. By providing information about pumping, which is in orange, there was a greater effect. We got 12% increase and then 30%. Similarly, we wanted to look at the effect on mean absolute error and RMSE. We can see that land use and pumping has interactive effect, because when we provide both of these drivers, there is greater reduction. However, pumping and irrigation demand has a relative higher impact compared to the land use change. I mean, in terms of physics, yes, we understand that when we pump water, it will change, it will have an impact on groundwater level, but I don't think that pumping will have greater impact compared to the land use, because pumping is there because of land use change, you know. Now just the summary and implication and future work. What we demonstrated here is that point-based observation and remote sensing can collectively calibrate and predict evapotranspiration with process and empirical models. For ET, even simple models like WISP can be biased, and we can use eddy covariance sites to improve those models. Empirical models based on a machine learning model can provide accurate estimate of ET, whether we want to predict it or forecast it, when we calibrate it by using a ground observation. And groundwater, which we know is very hard to predict, we can forecast it at well level using catchment related information. Now, based on some implication and future work, this modeling work, the modeling framework like that, can help policymakers to allocate water sustainably, and they can identify hotspots where we have high water stress. And there is a lot of promise now combining machine learning and ground-based observation to advance hydrological forecasting. And in future, I want to focus on like physics-guided machine learning, because that can respect law of conservation and boundary condition, and then the approach can be less black boxing. And then with growing number of eddy covariance sites over agricultural land and open data set from next generation satellite, we can calibrate and advance these models. And that is the end of my presentation. Thank you so much for listening. I would like to thank my colleagues, my committee member for their feedback, and my funding sources. Thank you very much.
Questions from the audience?
Hey, Ammara. Great talk. My question is that how this evapotranspiration and groundwater level change, like show up in the months of winter when it's snowy in Wisconsin, right? Do you still see some stuff going on in winter, or it's usually not too important?
I think it will not be because of, I mean, we probably don't see that significant drawdown because of pumping. But when, let's say, growing season happened a couple of months ago, the drawdown it can cause can persist for months. So it's possible that some irrigation that happened in a season and the flow path changes that it caused can persist there even during like winter and things like that.
With all this research that you did on water resource management and machine learning and remote sensing, what are you planning on doing next?
So,
Yeah, I have a postdoc offer, so I will be using machine learning model too, but now it won't be the agriculture area, and the focus will be more on forest side and carbon. I will still be working on ET, but then I will also include some research for carbon cycle, forest carbon cycle and evapotranspiration. And I really want to work on physics-informed machine learning models, like how can you add an entropy function if you are violating any law of physics, like water balance equations. So that I want to work on.
yes, you'll be heading over to work with Jackie Mathis at Harvard University at Harvard Forest, which is where I left from this work. Which is very exciting. Yeah.
Hi Ammara, really interesting work. I had a question. So I guess like in part A, you were finding that in the WISP model it was overestimating, and you were linking those overestimation to like how the model uses emissivity and LW-net calculation. And then I was wondering, like, where does emissivity or LW-net rank in part 2 when you use that machine learning algorithm and like all the different factors and how much they account for variance? Where does emissivity rank? And this like part of broader question also related to your future work. Like, can we use these machine learning algorithms to improve our, can we understand and like improve our process-based models also, or not, or is that, or like do you need more work?
Yeah, so I think the second part, I use NLDUS and that use Penman teeth, but there are some land surface model that use that ITSO equation. For example, we have Hydrus model, there is GLDAS model that use that ITSO, and I have a slide where I'm going to show you something about that. There's so many tables. Yeah, so you can see that I think it's very important to evaluate that emissivity at different location. For example, here, I mean these are our values. My updated value was 6.4 and 0.54, but then when it was updated in a different region, you can see this is a really small value. Here it's like -3. Then on a glacier, okay, on a glacier I understand that was -3, but so you can see that range. Oh, okay, we have a lot of -5, but we also have -3. So I think it's it will be nice to look at other emeriflux sites and other region, not only crops but also forests, and see that how biased the estimates are, and like regionally calibrated. I think that will be helpful because many hydrological models use these physical base equation to calculate the evapotranspiration. So I think that. Yeah.
Your questions?
In the third part of your work, you use the LSTM, right? How can you use that instead of random forest? If you, in the second chapter, you said like the random forest perform better.
Yeah, so for the third part, first I started with a simple deep learning method, not recurrent, just neural network. The model performance wasn't as good as I did LSTM after my prelim. I got some feedback from my committee member. Initially, I was doing groundwater levels. They said maybe you should subtract the effect of elevation and focus on groundwater anomalies. So I thought to myself, okay, I'm rebuilding the model. So let me just try doing random forest and then convoluted neural network and LSTM. So I tried all those, and LSTM was better because I think it also, because groundwater, that memory effect is more important, I think. That's why. And LSTM has that capability that CNN doesn't have. But I have read chapter where CNN, convoluted neural network, is a great model. Not recurrent, still neural network. It's good for imaging data. So I think it depends on the type of data. Of course, I can't say that LSTM will always work. It depends on the data.
For one more.
Yeah, building on that question, I was also fascinated to see that the pumping had a higher impact on your model improvement. And I'm curious, did you see a linear increase in just pumping water in Wisconsin over time? Like, why do you think that was so high in the climate model and not the LULC?
So like what you're asking, why pumping is more important than land use?
Yeah, and whether did you see an increasing trend in pumping in general in Wisconsin or not?
Yeah, I think with time, every year there are more wells that they're introducing. So there are more high capacity wells. And then irrigation is expanding. So yes, over time there is more, the depletion effect is becoming a more concern. There is a person named Sahu. She used, I think, Fourier transform based learning and studied about aquifers in Texas, and they also found that pumping seemed to be more important compared to land use, because in Texas too, two of the aquifers I think they looked at, so that one effect. So I think it's less, pumping is like more sudden, it's quicker than land use is like 1 year. Okay, so it's more on a year level.
If there's not anything else, we've got a few more hours to ask questions
I
into
think maybe
committees,
there is,
so we should get a little bit of a break before we switch to that. Let's give another hand to Ammara.
I'm just going to check if we have anything on Zoom. Can everyone hear me on Zoom?